a quite significantly different result than had occurred in the 1979-1981 timeframe. In particular, the National Research Council, the Aeronautics and Space Engineering Board, looked at the overall technology roadmap. They did not consider, is there a market for solar power satellites? They did not consider, is there an in-space market for high levels of solar energy in the Earth's neighborhood or the inner solar system. They only looked at the credibility, the feasibility, the kinds of cost numbers, the programmatics of the strategic research and technology investment portfolio that we had articulated with this steady stepwise progression of clearly identified and individually valuable demonstrations over the next decade or two. And their findings were that one, that it was in fact a credible plan, that it did allow you to make progress towards the goal of power for terrestrial markets, that it did so in such a way that it had significant, potentially important applications with civilian, military, and commercial applications, and that a flight demonstration was a reasonable way to focus the conclusion of each round of technology research and development, i.e. that rather than sort of making progress in the laboratory indefinitely, sort of at the end of each round of each cycle of innovation, that you should pull these new technologies together, sort of put up or shut up, and get them into a flight demo at these increasing levels of power and increasing levels of technology. So where are we in terms of the achieving the goal of terrestrial power? Where we are at the moment is basically far from it. I.e. achieving power at a competitive price. Now, this is setting aside the question of whether or not over the next several decades, due to a variety of factors, the cost of energy were to somehow become significantly higher. We are, in fact, based on an independent economic analysis, driving all of the research and technology planning towards 5 cents a kilowatt hour. So that's the gold star. That's the thing that we're driving the research and technology planning toward. So just as been discussed here, if it can't produce a terawatt, don't talk to me. Our objective is if it can't at least have a shot at getting down to something like 5 cents a kilowatt hour, don't talk about it. And where we are now is it's analytical. We haven't obviously done any flight demonstrations and so on. But nevertheless, we are still significantly far away. There are several companies on the internet which are trying to raise money to begin building solar power satellites. Let me urge you, if you get a phone call from a solar power satellite startup company, please don't buy stock. It's quite premature. I had a very good opportunity to leave the government and become an advisor to such a company. They promised me a reasonable amount of money, although not nearly as much as I hope to make by staying in the government. Nevertheless, I would not advise it. So what would a good concept look like? So the right concept, and we're still sorting out exactly what this would be and how you might approach it, but almost certainly it's in the RF case. I'm not going to talk about the laser case, although that's another strategy that one can pursue. In the radio frequency case, the phased array has to be extraordinarily low mass per unit square meter. All thermals should be local. You defeat the whole purpose of modularity and self-assembling systems if you have to take thermal loops over hundreds of meters or kilometers of distance. All power management and distribution should be local. You don't want to ship gigawatts across hundreds of meters or kilometers of distance. The diameter of the phased array transmitter should be extraordinarily large, i.e. at least a kilometer, preferably several kilometers, in order to reduce the spot size on the ground, and it needs to have subarrays less than 1 wavelength in size in order to provide adequate electronic beam steering and allow you to have the option of multiple beams going from one transmitter to different locations on the surface of the Earth. I think there are a variety of obvious linkages between this and the kinds of things that are kinds of technologies that are being developed in the MEMS and the nanotechnology field. Certainly in the development of extraordinarily lightweight structural systems. One of the issues with modular systems, of course, is that as you go to modularity, you have more interconnections. So a self-assembling system is likely to be somewhat more massive than a stick system, a stick-built system. You see that, of course, in modular homes versus stick-built homes. And so that drives you towards advances in materials to get these masses down. However, there are also requirements for a wide variety of advances in devices. The higher the temperature of the electronic devices while maintaining good efficiency, the more likely it is that systems like this will ultimately become viable. And the reason being that you can move in the direction of very large, lightweight, thin film structural systems for the collection of the incoming sunlight, and relatively small, compact, active systems for the conversion of that sunlight into output active phased array beams. Some of these goals that would have to be achieved, very large lightweight thin film structures, less than 10% of the total system mass, PV efficiency on order 50% or more. I'd be happy to talk about that during the break as to whether or not that's a viable goal. We believe that it is quite viable. RF transmitters of several kilometers in size, and so on. And with the goal, what we're shooting for is on the order of $2 to $5 a watt installed. And we don't actually believe this is an entirely unreasonable topic or a reasonable objective, in that if you look at it in terms of the masses involved, this is a device which is approximately like that, i.e. the total mass of this device, although it puts out a substantially lesser amount of power, and the production scales, i.e. hundreds of thousands of these kinds of devices, and the amount of intelligence involved and so on. This is approximately one of the elements, an active sub-element in one of these extraordinarily large phased arrays. You just need 100 million more of them. Some key directions: applications of intelligent systems, much higher strength to weight materials and structural concepts, higher temperature and solid state devices, both the PV side and the electronic side, applications of MEMS, and various options. Some whatabouts in a few seconds. Terrestrial power, solar power, there's the argument associated with the insolation. This is all going to be in the package that you'll have available on the website, so I won't go into it at length. The basic argument being that if you can compete effectively with terrestrial energy storage, then solar energy from space becomes a viable candidate. And if terrestrial energy storage becomes dramatically less expensive, then you don't. And that's just a straightforward trade. Low-cost launch, this is another discussion for the break. The fundamental issue with any transportation infrastructure is traffic. If you have only one car going across the Golden Gate Bridge, you can't afford it. And so it's a chicken and egg situation. You never have low-cost launch without large markets. You never have large markets without low-cost launch. We believe the stepwise strategy that we've envisioned, in fact, goes some direction to getting to an evolutionary path that gets us to the chicken and the egg more or less simultaneously. And the safety of power beaming, you can't see this very well. We're continuing research here. So far, all of the studies suggest that microwave transmissions from space are dramatically less dangerous than sunlight. Certainly the wavelengths are such that you don't induce bond breaking, and you don't get cancers induced. You get thermal effects if you're at the center of the beam, which you can protect from. At the edge of the beam, the power levels are well below the U.S. safety limits, most of the international safety limits except for Russia. And we're continuing research. Basically, the studies so far suggest that for both individual fauna and flora, that there are no noticeable effects due to the microwaves, other than the fact that the flora like it. They grow more quickly. So there's a lot of work has been done. There'll be more material in the backup charts that you can take a look at. It does appear that technically space solar power is quite viable, providing extraordinarily large, certainly hundreds of gigawatts, potentially the many terawatts. Depends on the size of the transmitting system and the type of orbits that you can place it in. We've made a lot of advances since the 1970s. We believe that there are very strong space applications for the component technologies and the systems which lead to an evolutionary roadmap that might in fact allow us to get to the point, not today, not in 5 years, not in 10 years, but at a point in the future where we could in fact decide whether or not these were systems that we wanted to add to the energy mix during the coming century. Thank you very much.
Again, while we switch over, take a question. Right here.
You said that one of the issues was the cost of putting stuff into space. It's pretty simple. You said one of the issues was the cost of putting stuff into space. What's the present cost and what's the needed cost?
It depends on the system that you're flying on. I'll give you two examples that are the extremes. One is the Pegasus. It's a small air-launched rocket. It was developed for DARPA, and it provides the launch of about 1,000 pounds or so on a priority basis, and that's about $25,000 a pound. Down at the other end is the Long March and similar Russian launchers. They're down at around $1,000 or $2,000 a pound. In between, you have the U.S. launchers, which are about $5,000, $7,000 a pound, except for the space shuttle, which is really a function of how often it flies. And with current payloads, when it flies again, it'll be up around $10,000, $15,000 a pound. So where we are in terms of the cost per, the way I try to couch it is essentially the cost per kilogram installed. So you take it as a total value problem. The central issues are getting it into orbit, getting it from low Earth orbit up to an operational orbit such as geostationary Earth orbit, and how much did it cost you per kilogram. That number, that package number, wants to be something like $1,000 to $2,000 per kilogram if you're going to win. And if it's not, then you lose. So the objective for Earth to orbit, the Earth to orbit part of it, has to be costs on the order of $100 a kilogram to low Earth orbit, so that your price, and I was giving you price numbers a moment ago, the price is on the order of a couple of $100s per kilogram, which is equivalent to about $400 a pound. So it would be about a factor of 5 reduction below where the Chinese are, on the order of a factor of 20 below the space shuttle.
Do you have a quick question, maybe?
Just quick, only a little bit frivolously, given that launch costs per pound dominate this whole calculation, how does this trade compare to launching an unshielded nuclear system up into space and not having to isolate the heat and just beaming back the power generated that way?
As it turns out, the specific mass of most nuclear systems the way they stand right now, and that's not really taking into account things like shadow shielding for human crews, is basically only providing shielding for their own electronics and the thermal management system. The specific mass of those kinds of systems today is on the order of 20, 25 watts per kilogram. Looking towards very large systems, more advanced systems, they think they could maybe get to 50 or 100 watts per kilogram. Given these strategies of hybrid large thin film structures with smaller multi-band gap cells, we're currently today in my office, you want to come to my office, I'll show it to you, at 200 watts per kilogram at the PV side. It's extremely unlikely that you'll ever be able to defeat the sun in the inner solar system in terms of watts per kilogram out of any of these kinds of systems. Because you ultimately have the problem of the PMAD and the thermal, and even though you go to the nuclear system, you still have to distribute that power across the backplane of the phased array. It's a bad solution compared to just using the natural sunlight.
Thank you. Thanks again, John. Next speaker is Dave Criswell from the University of Houston.
I'd like to thank the organizers of this, and especially Professor Smalley, for the invitation to talk with you today. It's a very interesting meeting so far. I look at energy in a somewhat different way. Instead of looking at how you extrapolate existing systems, once I read the paper by Goler and Weinberg in '76 in Science on the age of substitutability, I got to looking at it from what do human beings need. Right now, we have an existing global power system that supplies 1 billion rich people, we're rich, with the electric equivalent of about 2 kilowatts electric per person. That leaves the other 5 billion poor people with about 0.6 kilowatts electric per person. And this is equivalent, when you add up all of those, multiply out all those numbers, to about 220 million barrels a day of oil, or about 4.8 terawatts electric. And I'm just using the factor of 3 conversion from thermal to electric. And what I'm trying to do is put as much of this stuff in the same set of units as possible to reduce billions of barrels and millions of cubic feet, and all those conversion efficiencies are terms down to a common term, terawatts electric or terawatt electric years. Now, the problem with the existing systems are that they're not renewable, they are polluting, they depend quite often in politically sensitive regions, and they're too expensive for 5 billion people. Now, a needed global power system is one in which we provide at least 2 kilowatts electric per person. So right now, 2 kilowatts times 6 billion people gives you about 12 terawatts electric. A terawatt's 10 to the 12th watts. And so we have a problem right now. We've actually had a problem for 100 years. By 2050, with 10 billion people, we may need well in excess of 20 terawatts electric. And this is about a factor of 2 more than the largest number you've seen so far from Marty Hofford and others that work on the derived data from IPCC or from the World Energy Council reports. Now, this power must be clean, it must be safe, it must be affordable, it must be dependable, it must be sustainable. That means that century after century after century, you've got to keep supplying it. I think the solution is the moon. We are in a hydrogen economy, but it's because the hydrogen fusion burns in the center of the sun, going into helium and the higher elements through the carbon bicycle. The sun sends 13,000 terawatts of solar power reliably to the lunar surface. The idea is that bases on the 2 edges of the moon, these would work in pairs, convert the solar power to microwave beams. You see a beam illustrated. And then those beams deliver the power to the rectennas on Earth, as John Mankins described earlier. This appears to be quite safe. It would operate at about 20% of the intensity of noontime sunlight. And you choose a frequency range, preferably on the order of 10 to 12 centimeters, that passes reliably through almost all weather conditions. The extreme would be a 10-inch per hour rain, which we do see here in Houston sometimes. That kind of intense weather would give you about a 30% reduction in ground level received power, so you just simply crank up the beam from the moon. Now, the rectennas on Earth demonstrated back in the 70s, mid-70s, that convert the incident microwave into electricity at even then greater than 85% conversion efficiency, and then deliver the electricity to the power grid locally and regionally. A point about this, which would probably be asked, so I'll address it now, is this is a new flux of energy coming into the Earth, into the biosphere. It's net new power, so it can produce net new wealth. Will that produce heating? And the answer is no. The greatest amount of the energy goes out to the end user, is used and goes back to space as infrared. The part that is not converted is waste heat on the rectenna. You can simply put white rocks or paint the rectenna area white, and over the course of a year reflect out adequate low-quality sunlight to balance the heat input. Power beaming is not a gee whiz Star Trek Borg thing. It's actually a form of industrial strength radio astronomy. The Arecibo dish down in Puerto Rico is also a radar transmitter. The picture you see there of the moon, the south polar region of the moon, which you couldn't photograph in visible light, is a delayed Doppler image of the moon taken by Arecibo. Arecibo regularly can image the moon. Moon to Earth beaming is certainly a reasonable extension of existing technologies, such as demonstrated by large phased arrays, and especially demonstrated in the receive mode by distributed arrays such as the very large array out in Socorro, New Mexico, which is its maximum extension is about 30 kilometers across and operates without people. They go out and calibrate it about once a month. There's only 2 or 3 people at the array itself. The rest of them are in Socorro. And they calibrate it by looking at quasars, and they use quasar location to pin down where the actual antenna elements are. This is what the moon might look like with late 80s or 80s level technology for the collection of power on the moon, 10% more or less efficient solar cells, and you go through a long daisy chain of engineering efficiencies going from sunlight and free space to power coming out of that rectenna on the ground. One thing I did not mention, and I should back up and mention, is that the rectenna would only receive power directly from the moon when it can view the moon at more than about 30 degrees above the horizon. I will not go into it here, but an integral part of this to provide load-following power are microwave-to-microwave relay satellites in orbit around the Earth that would then bring power down to the Earth to a rectenna when it could not view the moon directly. But with a lunar system set up to provide on the order of 20 or 30 terawatts electric to Earth, this is about the area of the moon that you would appear to occupy with bases. These bases would appear to be on the order of 100 kilometers across. They would be built in pairs on the 2 edges of the moon, so one or the other was sunlit. During a new moon, You would provide power by having power lines across to the back side of the moon, about 500 kilometers across to the far side, where you'd have just photovoltaic arrays connected by power lines that would bring the power back to the earthward side. And that way you would have continuous power out of one side or the other. The only time you're out is during a full eclipse of the moon by the Earth. The same face of the Earth always, same face of the moon always faces the Earth, and so these arrays can be relatively static, and I'll get into their nature, but this would be an example of a harvested moon. The bases are built using known lunar materials in the known environment. Now, going from the Earth and looking to the moon and looking back from one of those bases to the Earth always stays within a couple of Earth radii of the same location in the sky. So the Earth is more or less fixed in the sky. A given base is composed of a power plot. A power plot is composed of solar arrays, that's number one, might be the area of the size of this room, and those in the prototype model that I'll be talking to you about in the next few minutes. These arrays would be just sitting directly on the lunar surface. You've got no air, you've got no water, you've got no chemicals to attack them, so things a fraction of the thickness of a sheet of paper can last there for decades. But you're building essentially very thin films directly. Those would be connected together locally with iron or aluminum wires buried under the surface where they're completely protected from the solar wind, gathered at a microwave transmitter, that's item number 2 at the end of a power plot at the earthward end, and then that illuminates a reflective array, number 3, and you replicate that basic power plot in one of these areas that looks to be about 100 kilometers across. It's actually 100 north-south by 600 kilometers east-west. And you arrange all of those reflectors so when viewed from Earth, they appear to fill one of the circles. And that then gives you a filled array which can project extremely well-defined beams back to Earth, a bore sight accuracy of about 3 meters. And what makes this practical is you don't bring the pieces from Earth. What you do is bring the production machinery. That would be items like number 4, the glass maker and the rover, number 5, assemblers, and then stationary plants to do the more intricate production and assembly of small parts and electronic parts. When Bob Waldron and I first thought about this and got into doing the modeling, we had an intuition that this would give you a very large multiplier effect, increase in efficiency, increase in output for every unit of mass that you brought from Earth. In the late 80s, in support of the Lunar Energy Enterprise Task Force, I went in and modeled all of these industrial processes using data from the 70s studies of building solar power satellites. For the bottom line out of that was that assuming the same technologies, operating technologies as the 70s power satellites, you produce 50 times more installed power than you did shipping satellites up from Earth. So a factor of 50 advantage in productivity makes the whole thing much more interesting. Now the next slide I'm going to show you, though, it goes past the demonstration, and it assumes that since you have access now to substantial electric power on the moon in various locations, and you have the ability to work with the common soils, the metals that are in them, the glass and the production and these sorts of things, that with careful industrial design, you can design about the production equipment so you can make about 90% of that out of the local lunar material. So this is the second step up, and what's important about that is it lets you get into exponential growth. And a ton of material taken from the Earth to the moon in the form of production machinery and manufacturing capability then results in several thousand times more energy delivered over a life cycle back to Earth. Now we've modeled this in terms of a life cycle for a power system. We even from the first took a relatively long view. So the particular model we're talking about here is a startup model where you start zero installed power. You go through an R&D phase of about 10 years. You go through a demo ramp up, and then by about 12 to 15 years into the project, you start building at large scale, and you install about 500 to 600 gigawatts a year of power that's received at Earth, and you do that until you achieve your 20,000 gigawatt or 20 terawatt output at Earth. And then you maintain that system for another 30 years, and under that curve of the power profile, you deliver a total energy of on the order of 1,000 terawatt electric years. Again, this assumes 90% local manufacturing, and this is a model in which you have quite a bit of labor done from the Earth through teleoperation. And we've gotten down into the manufacturing details enough that we can talk about distribution of machine mass versus the various functions such as micro-manufacturing, hot forming, beneficiation of your soils, construction of these are the materials you have to bring up from Earth, and then you increase those by local lunar materials by a factor of 10. So the total, for this particular model, the total mass you take to the moon, most of that over the first 30 years is about 60,000 tons. This was in a factor of 10 of pushed uplift, world uplift capacity now, and would also require maintenance of about 400 people on the moon and another 50 in Earth orbit for logistics, and in lunar orbit, and about 60 in Earth orbit for logistics. Now, when you put all of the numbers together, put them in $2,000, that's about $0.8 trillion over the 70-year life cycle, about 75% of that during the build-up phase. On the order, and this is approximate, 12 to 15 years to break even. Now, to put this in perspective, that's the $0.8 trillion is about 2 years of DOD budget, and that'd be about half a 1 year of DOD budget to get you well past break even. The rectennas that we assume on Earth are a specialized form called reflective arrays that were actually looked at by Rockwell and costed out. We reworked those numbers. And when you put them in today's dollars, 10 to the 5th square kilometers of these reflective arrays would be enough to receive the 20 terawatts. These would be split up into receiving elements, many thousands around the Earth, put where you need it. And that again would be about $0.8 trillion. It works out to the order of a cost, engineering cost of the energy of about 1/10 cent a kilowatt electric hour. Total revenues would be about $80 trillion if you're selling this energy at 1 cent a kilowatt electric hour. That revenue does not include the clean energy premium or dual use of the rectenna areas. So we'd be looking at an energy cost reduction by a factor of 10 to 100. This would allow then the developing nations to participate in the energy revolution of the developed world over the past 200 years. It offers fast capacity growth and profits by exponential growth of the power plot simply by putting in multiple production units as you get past the demonstration phase. Think of this more like road building equipment than some central Intel factory. The beam power itself can drastically reduce the cost of space transportation between low Earth orbit and the moon, and the cost of space operations, because you can now have your electricity at the end of a very unusual massless electric extension cord. Low rectenna cost and dual use of the rectenna sites would greatly enhance the economic development of developing nations. This would be net new energy that's delivered to Earth. It would be an energy payback on the order of a month, both on the moon and on the Earth. Would enhance the value of large international investments in developing nations, because you would now have the energy to start creating wealth. It'd be somewhat like happened with TVA or Bonneville in the U.S. back in the 30s. And if you can increase wealth in direct proportion to the amount of electric power that you bring in, electric energy you bring in, it's reasonable to expect world wealth to increase by about a factor of 5 by 2050. Considerable environmental advantages to this. There's absolutely no greenhouse gases, or not absolutely none, but essentially trivial. Fuel spills, nuclides, dust, industrial waste, they're just not there. It eliminates the need for hazardous facilities. The rectinas themselves are aluminum and silicon, can certainly be recycled if you have to get rid of them. Extraordinarily important as we are now a race that operates on a global scale. 20 terawatts is equivalent to 60 terawatts thermal. The geothermal output of the entire Earth is only 30 terawatts. We actually move more material by man's actions than nature does. Mount St. Helens, when it blew, was 6 weeks of industrial output of terrestrial society. It then enables us to have a source of power that is independent of the biosphere. This then enables with the access to independent biosphere, independent power, and net new power to remediate past environmental damage, the actual clean recycling of goods and non-polluting services and transportation, and it enables planetary protection. I won't get into that right now. There are very interesting possibilities with respect to nanotechnology and energy in this. First, addressing the terawatt barrier. Well, the moon has a potential of 13,000 terawatts, and I think we can tap more than a terawatt electric within 15 years. We thought of this back in the late 70s, early 80s, and it was clear to us that there were no technology barriers. It's basically an interesting industrial engineering challenge of bringing of using thin mass, producing thin masses on the moon, and then later getting into the manufacturing of production equipment on the moon. That gets you into exponential growth. Nanotechnologies may enhance this growth rate and lower the transport costs. Tethers are a point of particular interest for low lunar orbit to moon transport. Another interesting aspect of this is space and the moon provide a safe environment within which to demonstrate nanotechnologies without worries about biological interactions. Cost issues, well, I see this as analogous to what the U.S. has been doing for many years, from when George Washington built the first canal out to his property. The government must return to the moon. We could certainly do that within 8 years with a focused discipline program. There is then, and it would be like putting in the interstate highway system. Government to industry transition, new industrial practices rather than putting all of the resources, say an oil company putting all of its resources into downhole operations or operating under the seafloor, they would have to start working on the moon. This slide was provided by Professor Alex Ignatieff over at UH, who directs the Texas Center for Advanced Materials, and it's one of the concepts they've looked at for producing lunar photovoltaics on the moon. They did demonstrate over 4 years ago reasonable efficiency PVs on actual lunar material that was melted in the laboratory. They have gotten into the demonstration of nano layer techniques and solar cell conversion that could be used on the moon. The primary economic challenge in this is reallocation of microwave spectrum, because this will be a noisy system in certain bands. But it does offer the opportunity, the option, if you wish to take it, of sustainability measured in the multi-billion-year time scale, and give us the tools to protect and nurture the biosphere. The LSP is understood. It's based on over $1 billion of space power and lunar studies. Most people don't realize it, but we've spent worldwide over $1 billion understanding the moon. I administrated the review of the first 3,500 proposals submitted to NASA for lunar science, so I'm very well aware of this. In our models, it was profitable with 80s technology, can enable sustainable global prosperity, and if we had stayed on the moon during the 70s, this could have been started in 1980. If you'd like to dig deeper into this, there's a very good book, which I think Professor Smalley actually uses as his textbook for his class here at Rice, Innovative Solutions for CO2 Stabilization. I have chapter 9 in that. I've got a copy of the book I can leave on the table here if you'd like to look at it. An industrial physicist article that was published, this American Institute of Physics, that was published in 2002 and within 6 weeks was downloaded 18,000 times. And then 2 extensive papers that are available immediately online at the World Energy Congress websites. That's the 17th Congress here in Houston, which is the first place I heard the phrase, the Stone Age did not stop when they ran out of stones. And then the 18th World Energy Congress in Buenos Aires. Thank you.
A couple of questions while we're switching over. One back there.
I'm a little bit curious about the effect of meteorite or high energy cosmic rays on these lunar facilities.
The question is, what is the effect of meteorites on these facilities? The average erosion rate on the moon due to meteorites is 1 millimeter per million years. The lunar soil is a fantastic, out-of-this-world material. You go 20 centimeters down, and the diurnal heat variation goes from 400 degrees Kelvin to 1 degree Kelvin. A few centimeters of it will protect you from solar cosmic rays. 3 meters is as good a protection as our atmosphere provides.
I have a simple, maybe, question that I think I intuitively can sense the answer to it. But when you transmit large amount of power through the ionosphere, understandably in a very different frequency range, have you considered some microwave ionosphere interactions and what it may do to the ionosphere? Because it's a very delicate balance up there.
Well, the question is the effect of these microwave beams on the ionosphere. This was people started looking at this, of course, in the 70s with tests at Arecibo, both with the big dish and with an interferometric array on the side. And it appears when you're, as long as you're below about 1 kilowatt per square meter, there's very little effect. Down at what I'm talking about, the main interference is absorption by water vapor, which in normal atmospheric conditions is less than 1%.
Okay, I think we need to move on, and we're going to switch to fission and fusion now. Thanks, David. And Ernie Moniz from MIT is on next.
Okay. Take more questions.
There was one question. You had one more question for David?
David, you and the previous speaker were in some ways in extreme opposites. The previous speaker went from 1 kilowatt to 10 kilowatts to 100 kilowatts every 5 years, whereas you're going to, I think, take us to 10 terawatts on the first shot. Is there a sort of intermediate step where we can sort of get more confident and then get industry to be involved or something?
Well, we have to get industry involved because you've got to evolve away from the NASA approach of extremely high-tech pushing the limits to the generation of commodity products. And I think these can be demonstrated on the Earth very quickly. And then you're essentially going through the development of parallel production machinery. You know, it's like a seed, and once you can do the seed, then you can do many seeds. The phasing of the accumulation of the power itself from all of these happens out in the electromagnetic field in front of the moon. You're never handling in a physical way large amounts of power. And so I see no reason that this can't go linearly very quickly once you get confidence in it.
It's okay. It's okay. It's okay. Should we start? Okay, great, thank you. And I want to thank Rick Smalley for the chance to speak at Rice here a second time before he heads off to a safe research environment on the moon. What I will talk about today, however, is a technology that, as we've heard from a couple of speakers, is already functioning as, in fact, a very major energy source, nuclear fission. Why I'm speaking about this will become a bit more clear in a few minutes. But I did want to show, to start, part of the contextual information shown here. I'm also a Mac user, and I was on strike, but I have this overhead. This provides a context which is relevant in looking at the upside of nuclear power. What this shows here, it's a little bit hard to read, I understand, but basically it is showing the United Nations Human Development Index, indicator of quality of life in a certain sense, with annual per capita consumption of electricity. And basically the message here is that one sees here above around 4,000 kilowatt hours per person per year, one sees essentially the OECD, and then down with this very steep decline below this plateau, one sees, if you like, the rest of the world, with various gradations from China kind of here at about 1,000 to Ethiopia down essentially approximating 0. Now, the message of the next 50 years, presumably, is to see these countries, roughly speaking, marching up this curve towards a higher human development index. However, as they march up that curve, and there's a lot of people here in this, in this part of the curve, China, India, Indonesia, Yemen, number 18 in the UN projection for 2050, et cetera. As they march up, it would be not very sensible to treat all of them in the same way as candidates for being part of the expansion of nuclear power. So as I come to discussing what we believe is a rational scenario to address Rick's terawatt challenge with nuclear fission power, we can't discuss all of this, but we will be having a scenario that folds in many factors, including urban population, technical infrastructure, opportunity for the kind of capital investment required in nuclear power, et cetera. Now, the terawatt challenge for nuclear power, for nuclear fission power, if we take a terawatt of electricity capacity, I want to stress, that is approximately maintaining market share, global market share for nuclear power. Let's call it 20% plus or minus a bit, okay? So we're talking about a market share preserving if we're going for a terawatt. We've heard a couple of people, a couple of speakers, most recently Nate, talk about 10 to 30 terawatts. I will be stating as a conclusion of our analysis that we don't believe that even though it does not violate the laws of physics, as perhaps some other technologies that he discussed did, it violates various laws of economics, et cetera. And in fact, we will argue that a terawatt scale, maybe 1.5 terawatts, is about the maximum that actually you can imagine happening. So the terawatt challenge in nuclear power is a little bit different in a certain sense. We will argue it's a scale at which one does have a reasonable impact on important problems, avoiding a reasonable amount of carbon emissions, for example. On the other hand, we will also argue that you really can't expect to do more than that, even if you ever reach that kind of scale. So that's part of the context. With regard to the market share argument, let me remind you of world energy consumption by fuel source. This is hard to read, but it's fine. Bottom line is, I'm just repeating things you've heard in different ways. The non-carbon sources today, the blue bars, are about 15% of global energy use. If one takes as a guiding framework that, say, in 2050, one has, let's say, twice the primary energy use, which probably is on the low side of the scenarios, and that fossil fuel use cannot at least exceed where we are today in terms of various stabilization scenarios, roughly speaking, then you see immediately we're talking about an order of magnitude increase in non-carbon sources. That's the kind of challenge we're talking about. And I'm not going to be arguing that nuclear fission is the answer for that gap. As a contributor, a non-trivial contributor, potentially. That's kind of the framework for the discussion. Now, let me turn back briefly to this issue of the, let me call it the demand map, where, as one looked at that first curve, as countries move up that curve in terms of providing more electricity to improve the quality of their lives, their economies, et cetera, where might that be? Now, again, I will not be able to go through the analysis supporting this other than to have mentioned various factors involved. But I think there's often stated the idea that somehow a major global expansion of nuclear power in the next decades would somehow see nuclear power, to choose a word well, proliferating all over the developing world. The fact is, when you look at it, that is not a credible scenario. That is, this is one scenario for the terawatt electric, and what you see is, frankly, There's no way the world's going to reach a terawatt if the USA isn't driving the train. Developed world and FSU, about two-thirds, in this scenario, about two-thirds of the capacity. Developing world, the remainder. China and India, the big horses in the developing world. And then in this scenario, as you can see, about 100 gigawatts, Indonesia, Brazil, Mexico, South Africa, Algeria, et cetera. Now, from the proliferation point of view, which I will not discuss today unless asked in questions, an important issue, this is nevertheless not particularly comforting. We could go into details about that, but it is not as though the expansion of global nuclear power is somehow hinging upon an enormous profusion in the developing world. Lots of interesting issues here. Nate mentioned issues of public acceptance. This scenario would fly in the face of, let's say, at least the slope of public sentiment in a variety of developing countries. But the issue here we're discussing is, and let me frame it the way we have discussed it in a study that I will be in effect reporting on, is if the carbon problem in particular is a major driver of technology pathways, and if we want to preserve the option of nuclear power contributing on a scale that's meaningful, a terawatt, what kinds of actions would one be taking in a policy sense and in a research sense today to enable that as an option? It's not a prediction. It's not necessarily a wish. It's just a statement of where are we and how can we get potentially to this point. And the study I referred to, I should say, is one we're doing at MIT. John Deutsch and I are co-chairing it. I want to stress it is a group that does involve nuclear engineers, but as neither John nor I are nuclear engineers, we have policy experience, we have economists, Paul Joskow, political scientists. It's a broad group looking at this in this context of the carbon and the terawatt challenge. Okay. It's roughly speaking the getting enough gain for the pain of nuclear power to make it worthwhile. So let me talk about the gain part very, very briefly, just to make it more quantitative. Carbon emissions. Again, we've heard this in a variety of ways, but let me just make it explicit. If we take our baselines of coal and natural gas, and I've put in some assumptions here for efficiency, for example, then one is talking about roughly 1.8 megatons of carbon. I want to stress, not CO2, carbon per year from a gigawatt electric coal plant, slightly less than half of that for a gas plant. But that's the scale. So the terawatt scenario, let's say if you're looking at coal, as we have maybe been drifting towards one of the major elements of growth in electricity over the next half century, you would be talking about 1.8 gigatons, and obviously if it were gas, 0.75 gigatons, and you can dial whichever linear combination of that you wish in between. So that's, again, kind of the scale in terms of carbon displacement in that kind of terawatt scenario. Okay, so how do we get there? What's likely to drive one there? Well, first of all, what we have viewed something, a factor which was not highlighted consistently in many of the technology discussions as primary, and that's economics. It's very important that we look at the economics. Now, what I'm going to present is the result. Nate showed, I want to make it clear, Nate showed a price of electricity per kilowatt hour of nuclear, 2.3 cents. That is true today because of amortized plants. Okay? The relevant issue here is what is the cost, and I will state in a merchant plant model, of building a new nuclear, coal, or gas plant. Now, I won't go through all of this, but let me point out a few key parameters. Probably hard to read. It's okay. I'll tell you what's important here. These are our base case input parameters for nuclear, coal, and gas. There are several important issues here to which I will return. Number one, capital costs. The overnight costs, and I want to stress, this is now based upon research and hard-nosed experience, not upon promises. Okay? neither promises of the NEI for nuclear, nor your favorite coal person for IGCC or anything else, okay? This is experience. Maybe one can beat this, okay? But let's start with experience. Overnight costs, nuclear plants, $2,000 per kilowatt. Considerably less than the Japanese have spent for their last plants. One plant may have beat this, the Koreans. Exchange rates come in. It would be fair to call them, their last plant as built at around $1,700 a kilowatt. We have gas at $500, a combined cycle gas plant, $500 a kilowatt, and coal at $1,300, including all environmental cleanup equipment other than carbon, all the standard pollutants. Capital costs, big issue for nuclear power. Fuel costs, I won't go through in detail, but it's the opposite. Fuel costs for nuclear power are extremely small. Heat rate, unfavorable again to nuclear power, 10.4 versus 7.2 for natural gas. In other words, natural gas about 47% efficient in our calculations. Nuclear at about a third. And finally, and very important, if you want to be serious about who's going to give you money to build a plant, what do the bankers or the investment community think about the cost of the money? It is not the same for a nuclear plant as it is for a gas plant. So when you look at debt fractions and return on equity, it is unfavorable for nuclear power. All of this is folded into our calculations. So what comes out? Here's the base case. So with those assumptions, nuclear power comes out at 7 cents a kilowatt hour. Pulverized coal, 4.2. Gas at a $3.80 gas over the period of the plant, 3.8 cents. Gas, of course, has considerable uncertainty. Gas is driven by the fuel cost. It's exactly the opposite of nuclear. And so, as we know, the gas costs are maybe not something one wants to count on for a 40-year investment in the plant. And so there is considerable variability there. Now, very importantly, so we say, first of all, if this terawatt challenge is to be met by nuclear, you've got to get the 7 cents down. Here are some steps. O&M, operations and maintenance reduction. What we've put here is actually the current performance of the best performers. So that should be achievable, in principle. Construction costs, critical. 25% to $1,500, very important. Big drop in the costs. And then finally, I'll just skip down here to the cost of capital. If the cost of capital for nuclear power were the same as for gas and coal, it makes an enormous difference. With those, you could be down in the 4.4 cents. So these are very important economic issues that are going to determine much of the nuclear power trajectory. Another one, of course, is the externalities, as we have discussed, in carbon. If you now put carbon, however you do it, I don't care what the mechanism is, but if in the end you end up paying somewhere between $50 and $200 a ton of carbon, not carbon dioxide, of carbon, then as you can see, the coal and gas prices are impacted significantly. Bottom line is, there are a lot of uncertainties here. Nuclear power might be in the game as a serious economic competitor in terms of at least life cycle costs if the nuclear community works hard at capital costs and can get some confidence in the investment community, and particularly if carbon externalities are one way or another put into the equation. Okay? Now, what I said was our study is kind of looking at the issue of costs are critical. How would one enable this? And again, this is not necessarily a statement of or a prediction of what's going to happen in the Congress next year, but how would one enable this? First of all, look in the context of a carbon avoidance government incentive portfolio, you can say, okay, we have tax credits for efficiency, hybrid cars, whatever. We have a program, let's say, on coal/sequestration, future gen plus sequestration. That's what that area needs. It needs a serious research and demonstration plant and sequestration. That's tailored to that. You go to renewables, let's say in wind, you have 1.7 cents per kilowatt hour for 10 years. which, by the way, is a humongous subsidy. For a gigawatt electric plant equivalent, that is $140 million per year credit. If you go to nuclear, what one probably needs, if one wants to give this a kickstart, is an upfront cost sharing of what you would call first mover costs. Because right now, there's a good chance those capital costs could be real, but you can't get over the first hurdle to start building a new group. If you were to put in somewhere between $100 and $200 million per plant for some number of plants, 5 or 10 plants, that would probably answer the question once and for all whether nuclear power is going to be competitive. And I would just note that that kind of scale corresponds to the carbon cost of 1 year of a coal plant operating at $100 a ton of carbon. So I just leave that with you. That's an example of the kind of policy initiative you can evaluate 10 to the minus what in terms of it happening as a policy route to answer what is probably the key question if nuclear power is going to take off and be on a terawatt track for mid-century. Okay. Now, let me, that took a lot of time, but it was the main point. Let me run through some other points. There's a lot of discussion in the nuclear professional class. There's a lot of discussion about what we really need are advanced fuel cycles, recycled plutonium and actinides and all kinds of stuff. Our argument is that is not part of the growth scenario. Once again, the main reason is economics. If I got to struggle to get a light water reactor I've been learning to operate for 40 years down there, give me a break. A point for the aficionados, which we're not trying to explain, is I have a datum that proves it. If what I said weren't true, we would be disposing of Russian plutonium right now. That's possibly cryptic, and I can explain it later if you wish. Advanced fuel cycles cost a lot of money. We do support a basic research and engineering program looking at that big technology phase space before we get trapped into another Clinch River, which will screw it for good. Excuse the German. So now, we do believe that there are evolutionary thermal reactors which could be very interesting in the growth scenario, and one was mentioned yesterday, and that is the gas reactor. There's an example of an evolutionary technology of which we have some experience, which in 20 years could be real. It's much more efficient. It's probably the best waste minimizing thing we have because it's much more efficient in thermal conversion. It has passively safe features, which are very nice. It has some fuel form issues that are very nice, small micro pellets with a carbon composite coating that have attractive issues for safety and for proliferation, actually, and for other issues. So there are some real technology evolutionary paths that could be important in this growth cycle, but probably not very fancy so-called breeding closed fuel cycles. And in that context, and we've checked our notes, we agree, in that context, by the way, let me just make sure we all understand, there is no uranium constraint for that scenario going to a terawatt electric by mid-century. Finally, waste, of course, in this scenario, I won't talk about proliferation and safety anymore. Waste is a huge issue, obviously, another possible showstopper. The real remaining advantage discussed for the advanced fuel cycles is their ability to give you a better waste problem. Those statements, I believe, are considerably exaggerated. The volume reduction benefit is, to first approximation, a fake, because you have all the fission products per kilowatt hour you had before. You've taken out the uranium, which is not the problem. Secondly, they would give you an advantage in terms of removing the actinide load for the very, very long-term problem. Whether the public cares about that is not clear, but it would certainly reduce that. However, summary statement, our view is that we have no reason to question that geological isolation, properly executed, would not already be quite adequate. for that task. And third, we believe there are geological solutions that may offer a far greater advance in waste isolation than those other approaches do. For example, goes back to something, as Joran was saying, deep boreholes in appropriate locations can look very, very attractive for further giving you much, much more confidence in waste handling. So nanotechnology, I'll conclude with a few comments on nanotechnology. Of course, the bottom line of what I've said is that this is a technology that's already out there, and its growth trajectory is not so dependent upon major technology breakthroughs, at least at the moment, as it is upon other breakthroughs in economics, political acceptance, waste, etc. Nevertheless, although I was unable to find very much focused work in the nano area applied to these issues, the industry is worried about other things, certainly at the moment, there are some areas where one can imagine, I think, nanotechnology being interesting for the evolutionary path, and maybe even very far in the future for a much different path. One, of course, the issue of materials, of course, is ubiquitous when we talk about nanotechnology. High temperature materials, for example, the gas reactors, particularly materials that were radiation resistant, perhaps, and that does involve often the nanoscale questions, could be very, very important in terms of developing advanced reactors. A nano-structured fuel for those gas reactors could be very, very important. For example, if you could have the fuel have a temperature resistance even greater than what they currently talk about, you could imagine potentially moving towards a lack of containment requirement. Big economic impact. If the fuel itself were really assured of maintaining the fission products under any conditions in effect. Nanoscale modeling of materials is also important here. Problems like understanding cracking by linking nano to macro scales would be important in many areas, including this one. An area, however, which may be the most interesting for near-term impact, it seems to me, is potentially in nano-engineered, maybe with nanoparticles in a clay or something, nano-engineered barriers for a waste repository. A barrier that would be extremely effective at holding up the migration of any nuclides of which one was concerned. And then in the very far out region, and this was one of my colleagues, and I won't maybe embarrass him by giving his name, is in a brainstorming was the idea that potentially far future, a kind of a nano-structured fuel form that maybe even had, quotes, direct conversion of fission to electrons, something like that, which could be, again, have an enormous impact in the operation of these plants. But bottom line, again, I'm sorry it's not a great technological statement, but the bottom line is it's all about the economics at the moment and then about handling the waste. And then there is certainly no technology barrier to going clearly to this terawatt scale by mid-century. Thank you.
Okay, again, while we switch over, a couple questions right here.
Okay, just wait 1 second. Or else we won't hear it in the audio.
Could you comment in regard to the cost of estimating the decommissioning of the nuclear plants? There's a lot of numbers, and the companies are supposed to be setting aside money to do it.
Right.
But is the money that they're setting aside adequate, and what will it cost 20, 30 years from now when they decommission the plants?
Okay, let me tell you what we have in our base cost. And that's one reason why our cost of 7 cents is a little bit higher than what you see elsewhere, including in Melanie showed a banker's chart, which was qualitatively similar, but a little bit different. But for example, we include $350 million decommissioning per gigawatt reactor. Okay, so and that's all part of our cost structure. It's very important. We also include, by the way, a mil per kilowatt hour for waste management, which is the current charge. We see no reason for that to be the wrong scale, okay? It's one of those things, however, where you know how much it'll cost, but you don't know if it'll work. It's like sequestration.
Only a naive question, maybe out of my ignorance in nuclear engineering, but one way that we are using the oil industry in order to soften the big upfront sunk investment in capital is to go, and I showed this picture of the well that looks like a root system of a tree, to go into phase development. Rather than having one whack, there is an oil field, now you produce it for 30 years. Is there a way to phase developments of nuclear plants?
Well, there's two answers to that, Yoram. One is, of course, I think the scenario, as I laid out, is in some sense already much more of a phased development than you hear the professional R&D class discuss. It really is based upon an evolutionary, already the advanced light water designs and the cost controls and actually manufacturing techniques which are critical to be able to get those costs down. Then as one goes forward into the gas reactors, perhaps, an important thing I did not say about those is that their design would appear to allow you to be much more modular at a reasonable cost. So in fact, the current designs would be typically, depends whether you go pebble bed or prismatic, but let's say in the 1 to 200 megawatt range per unit, they operate with a much lower energy density as opposed to the gigawatt or 1.2 gigawatt scale, which is where you really get the economics, or at least the current economics, in light water plants. So there's a certain element of phasing in that sense while one thinks about what might come in the second half of the century. Can I make just one more comment? I'm sorry, I didn't get to it, but I should have said probably that another important factor in the discussion, which I skipped over, is that in the nuclear energy community, again the R&D community, I should say, really, the big rage right now, or one might say the newest straw, is hydrogen production. The idea is one, well, either two pathways. One, of course, is electrolysis, and it's with a non-carbon energy source. There, the issue is how much does it cost you for electricity? The second pathway is a so-called thermochemical decomposition of water, where you would need a very high temperature reactor. Many of us don't think the economics look particularly promising for that. But whatever the case, there is a big push in this direction. What I want to just maybe reemphasize is a statement we've heard a couple of times. You pay an awful lot of money to go through various transformations of one form of energy to another form of energy. In fact, actually, Nate, you gave a number about cost per kilojoule, per gigajoule of electricity at your house. Well, you don't live in Boston, apparently. I can tell you, in Boston, I use your strategy. I bring natural gas to the house for heat and for hot water because I pay about $8 or $9 a gigajoule delivered to the house. I pay $28 a gigajoule for electricity delivered to the house. Now, in the same vein, if we start talking about hydrogen to replace our transportation needs, 30 quads in the United States, and you start adding a factor on that, the disruption of the energy system is enormous. For example, not including efficiency factors, okay, to be fair, but if you do a pure energy equivalence of 1 million barrels of oil per day to the amount of electric capacity you need to make the energy equivalence of hydrogen, that is 125 gigawatts electric. So 125 nuclear plants, more nuclear plants in the United States to displace 5% of our oil use. Good idea.
Thanks,
I'll give you a factor of 2 in efficiency. All right.
Thanks again. We got to get the mic off. Okay, fusion, Dr. Robert Goldston, who is almost ready.
Good afternoon. At the very beginning of the session, maybe the second talk, you heard Richard Russell talk about ITER, I'll decode it for you, the International Thermonuclear Experimental Reactor, big international project which President Bush has requested that we join. And so you may wonder what's been going on with fusion that all of a sudden President Bush thinks he's interested. So I'll tell you about fusion energy. My particular expertise is in magnetic fusion energy, and so that's what I'll really concentrate on, holding on to hot plasmas with magnetic fields. So the basic process that is most likely to be successful in the nearer term, meaning in this century, deuterium and tritium combine, they make an alpha particle. That alpha particle has 3.5 MeV, which keeps this stuff hot. They also make a fast neutron. You capture that in lithium, and that provides the tritium, so you have 2 cycles that you need to keep going to make fusion work. And out comes electricity and perhaps hydrogen, although I don't think that's a near-term option. So why is it that you would be interested in this? And we've heard that there are a lot of disadvantages and problems with all the different sources of energy. Right up front, the problem with fusion is that it is not at this time practical. So let me say that maybe 3 times in the course of this view graph. But I'll say it once at the beginning, once in the middle, once at the end. But if we can make it practical, it has plenty of fuel. It's available to all nations. There's at least thousands of years' worth of this fuel, probably millions. It has no carbon emissions. The radioactivity, as I'll show you in a view graph, is relatively short-lived. It can't blow up. It's resistant to terrorist attack, essentially because there's very little fuel in the chamber at any given time, and it has very little afterheat. There's low risk of nuclear materials proliferation. I don't say no risk. You don't need to have any fissionable materials in a nuclear fusion reactor. There are neutrons. You could, in principle, breed nuclear materials, but it would be a matter of kilograms of nuclear materials being detected out of 0 rather than out of many, many tons. So it is a relatively easy thing. But now this is the time for me to say, but it doesn't yet work in a practical sense. It's compact relative to solar, wind, and biomass. We've seen land usage. People seem to think that giving up Arizona really isn't that much of a problem, but you probably ought to talk to the folks in Arizona. It's not subject to daily, seasonal, or regional weather variation, nor does it need to be located near a place where you could sequester carbon dioxide. So that gets you away from large-scale energy storage and long-distance transmission. We've looked at the cost of power. Of course, this is something that maybe perhaps it's like what Ernie was saying. It's a class of something that you can estimate what it could cost if you can do it. And we don't yet know for sure we can do it. But you can get to 5 cents a kilowatt hour kinds of electricity costs. And you could, in principle, create hydrogen. You can certainly create electricity if you can do it. Again, once again, it complements other nearer-term, now working energy sources. Okay, what about this radioactivity question? Here are 3 different materials that we are looking at for fusion. This one is relatively well developed. This is a measure of radioactivity. A more sophisticated measure actually is more advantageous for fusion. Years after shutdown, here is nuclear fission, and you can see that in 10,000 years you get to a certain level that people are beginning to worry about, but you get there in sort of a human lifetime from even the worst of the fusion materials we're looking at. And so you've kind of changed all of human civilization timescales for human lifetime timescales. And while we're talking about coal ash, it has some radioactivity. Actually, its radioactivity doesn't decay at all in this time period, right? It thinks in millions of years, coal ash. But the radioactivity from the coal ash you're planning on piling behind your power plant is comparable to the radioactivity from fusion, again, in sort of a human lifetime. So you could imagine some local storage, even recycling of these materials, particularly the more advanced materials from fusion. So it's a somewhat different question, I think. On the topic of hydrogen, here is the variation in electric production from the TVA. This is from a journal article on this topic. There's some pumping going on here. It's actually more different than this looks. Electricity demand certainly varies strongly during the day. Fusion systems have near 0 fuel costs. The hydrogen, the deuterium, are just, deuterium and tritium rather, really nothing. There are parts that wear out. But the off-peak operation, therefore, has very low marginal cost. And so you can do hydrogen production from the off-peak operation. Say you're operating here conceptually. This is your off-peak production. You can do local production. You can imagine thermal production, for example, or electrolysis.
But actually, I find the most interesting idea, so that you don't need a hydrogen distribution system, is to use the fact that the grid is also not doing too much at that time. Send the electricity out to the, quotes, gas stations and make them gas stations where they deliver the hydrogen. And it's a funny sense in which steady things, like regular fission also, can use this idea of hydrogen for peak shaving in the inverse of the way that wind uses it, and in fact, perhaps even more efficiently. Now, these are charts you've seen many of. This is the anthropogenic emission versus years. This is the buildup of carbon dioxide. It's hard for me to read at this angle. I think this is probably the 550 case. Okay, and you can see it takes sort of 50 to 100 years to level off, a couple hundred years if you get to some of these, frankly, more realistic cases that we're headed to. There are a couple of different scenarios. The IPCC scenario you saw in a few talks, the WRE scenarios you saw in other talks. What the WRE scenarios do is, are they more economic in that they allow the carbon dioxide to grow a little bit earlier and then level them off harder later. And now you look at these charts and we get ourselves really quite wound around the axle about 2050. Depending which of these curves you take, there's a lot of energy in that difference. But what I want to look at is the longer term picture. And the longer term picture is indeed that there's a big problem in 2050. And this is a 650 scenario. You have to understand that the force function is logarithmic in the amount of carbon dioxide in the atmosphere. So 650 is worse than 550. But and there's about a factor of 2 difference there, depending on that choice. And then you can also go down to a larger difference if you choose, for some reason, the IPCC scenario. But all of these, actually, where there is not uncertainty, Jerry Malman, who's director of the Geophysics Fluid Dynamics Lab, or was director there nearby us, pointed out that to me, where there really isn't uncertainty is out here. It doesn't matter what scenario you take, you need just humongous amounts of energy. So here's a picture. Here's what these look like. This is an economic analysis that points in this direction, that we need to be worrying about this 2050 and beyond kind of timescale. And indeed, here's just a look at fusion. This is estimated total primary energy consumption from the IPCC. I'm including things that are off-grid here to get total energy. If you just say, I want the 650 ppm WRE scenario, you're allowed that much carbon-based energy production at today's carbon intensity, or slightly reduced for this. And what you can see is that fusion is a little late on this scale. This doesn't come to 10 terawatts. Again, if you take the you take the other scenarios down the chart, you ask for 550, you ask for the less economically attractive IPCC scenario, you can get it up above, a little bit above 10 terawatts. But fusion with a reasonable growth rate, this corresponds to about 1 in 10 power plants being replaced with a fusion power plant, grows up here. Someplace up here, if you're going to contribute this kind of amount of energy, you have to be contributing to transportation. I don't think you're ever going to use electricity for heating purposes. That is really tremendously impractical, I think. But you can make significant contributions if, with nanotechnology and pushing a little harder than some of the scenarios we've developed, you move that back a decade, I can meet your 2050 goal to be on your chart. But I think you also have to think in the very long term, because that's very important. You're going to need concentrated energy sources, because world population growth is going to be in cities and megacities. Okay, so what is this all about? What are we doing? Well, as we've heard, the sun is a fusion power plant. It uses gravity to hold this very hot gas together. In nuclear weapons and in inertial confinement energy that I won't talk about so much, you use very energetic pellets, very energetic beams to compress a pellet and heat it so that it fuses before its inertia lets it explode, and that's why it's called inertial fusion energy. But what we do in Princeton, and what is the dominant process being looked at for energy around the world, and it is a very aggressive program around the world, you use magnetic fields which cause hot gas plasma that's been ionized to spiral around that magnetic field. Then you close that magnetic field on itself. The plasma spirals around this magnetic field. It can go for hundreds of kilometers along the magnetic field before it moves centimeters across. It's a tremendously effective way of holding this very hot gas in place. In fact, we've been to temperatures of about 1 billion degrees Fahrenheit with these gases and held the plasma there at those temperatures for many seconds. So this is a tremendously effective way of making these very hot gases. And just as an aside, the plasma science that went into some of this has had impacts way beyond fusion energy. Understanding astrophysics, every computer chip is processed with plasmas these days. Plasmas are used in space propulsion. Okay, what does a power system look like? You have a fusion plasma. It makes neutrons that goes through a material surface. This is where some of the high-tech nanotechnology might come in. You absorb it in lithium. That provides the tritium. There's plenty of deuterium around to go in. Magnets on the outside, higher temperature and higher field superconductors would be very helpful. Heat exchanger, turbine, generator, or you can use some of the heat and or some of the electricity for hydrolysis. That kind of a system is what we're looking at. And so what have you done for us lately? Here is energy in watt seconds, something even a congressman can maybe understand. So here's about a few millijoules. This is what they recently made in the experiments in Sandia. I did that in my PhD thesis. We figured it was enough electricity that if we made heat, if we put it into electricity, lit up a light bulb with a couple of millijoules, and your eyes were dark adapted, you could see it. So we chose to get very drunk. It was a huge success in those days. Now we're up at the 10 to 20 megawatt range of fusion power in these systems. Real power plants, obviously, are up here. But my own personal career has spanned that distance, and I feel pretty confident we can get up there. We've gone up sort of 12 orders of magnitude, while computers have gone up 6. We know computers on everybody's desktop, and there aren't fusion power plants around the corner. That's a big doozy of a step there that we have to take. And that's, to a significant degree, what this ITER project is about. And we get, as I said, some of the credit for the computer chip progress. So what is this international ITER project? It's a cooperative opportunity to make a sun on Earth. It extends the science. It lets us do very large plasmas that are the size, larger than the size you'd hope ultimately a power plant will be. It'll get us the experience of this self-heating, where the plasma, the alpha particles from the fusion reaction hold the plasma at temperature. You got some fusion-relevant technologies all around here, magnets and blankets. You're going to operate at a pretty high duty factor. Our present experiments maybe have a % duty factor. This will be 25% duty factor. You want to be 85%, 95% for a practical system, but that's a huge step for us. We've had a major impact on the design of this. It's not a power plant. Power plants are 2 gigawatts, 2.5 gigawatts thermal, but we're 600, 700 megawatts. That's no longer just playing around. Its pulse length is about 400 seconds. At a gain of 10, you'd like a gain of 20 or 30 for these things. And a 1-hour pulse at a gain of 5, that's not quite enough either. There's more physics to be done that we want to do in part in this experiment. But this is getting us a huge distance from 10 megawatts for a second, right? So the way that the international folks look at this, the international group working on this that now includes us, is to demonstrate the scientific and technological feasibility. It's not going to show that it's economic yet, by producing industrial levels of fusion power. So we're very excited about this international opportunity. Where does it stand? Europe, Japan, Russia, Canada have already been negotiating about this. The US and China have now joined. South Korea has made an offer. We'll see whether it's accepted by the whole team. There are 4 sites on the table: northern Japan, Canada near Toronto, Spain, Freedom. With the US and China, and probably now South Korea, the numbers may add up. Europe has talked about putting 53% on the table, and Japan has talked about 17% actually under those circumstances, and you don't take too much from everybody else to make it work out. Key issues are to resolve siting and cost sharing. This is a major international construction project. I should talk to my friends from NASA about the ISS. That seems to have been a challenge to keep it on budget and schedule. So that's going to be a major issue. Risk allocation is an issue. How do you handle contingency? Europeans can't translate the word contingency in English into European. So we have some work to do with them, because that's got to be taken very practically. Now, there's more work to be done in parallel with ITER to make fusion practical. The configuration of ITER is what's called a tokamak. It requires a current to flow in this plasma. You need to come up with ways to drive that in steady state. It also, I showed you, it makes about 500 megawatts. You need a real power plant to be a little bit smaller than that, and to make 2.5 gigawatts if you're going to reach the kind of economic challenges that Ernie talked about. So you need a higher pressure plasma in there, and that's what you get more fusion from. And so there's some work on active instability control to do that we're doing in the United States. There are other designs that give you very high fusion power at much lower magnetic fields, drive down the cost. We're looking at that. There are also configurations that don't have the problem either of instability control or of driven steady state. They're totally passively stable. They run in steady state. They vary in shape as you go around the torus, and their magnets are a little more complicated than this. So we need to understand that physics. So a question you could ask is, gee, if that's what ITER is and you need to look at some other options, why are you building ITER? And we struggled with that. We had one of these snowmass meetings like the high energy physics people do, a little bit of a, following some earlier analyses, a come to Jesus meeting. And we struggled with that question, and we argued about it, and the folks who are advocates of these other configurations talked, and we came to the conclusion that if we do domestic innovation along with ITER, then we can get there. And in fact, ITER will provide most of the science and most or all of the technology you need for the other configurations to be able to move forward towards a demonstration power plant. So that was a bit of a struggle, but is what was the technical conclusion. So this is being studied worldwide, this range of toroidal configurations being studied worldwide. Here is, I'll only show a few. This is in Europe. You see the man stands about a third of the size of the tokamak in Europe. Here is the tokamak at MIT, and they hire giants there apparently. Korea, China, India, and Korea, China, and India are each building $500 million fusion facilities. The stellarator, the configuration that varies around the torus, billion-dollar facilities both in Europe and Japan, some nice facilities at Princeton where I work. I won't get into that. What are the areas of technology that are critical for fusion energy? Let's start with this hot plasma in the center, and that's my job, that's the physics. But what about what we can do moving outwards? There's heat that comes out. 20% of the heat comes out, 20% of the fusion power comes out in the form of heat. 80% is neutrons that are absorbed in this lithium blanket. 20% comes out as ultraviolet radiation, energetic particles. You have to capture that on the surface. This is not a very good reproduction, at least from where I stand, of a tungsten mesh, sort of a brush of tungsten that can take 25 megawatts per meter squared in steady state that was developed for this purpose and looks very attractive. You need this tritium generating blanket. Out come the neutrons. You want to absorb the tritium. You want to have things in here like silicon carbide that allow you to run very high temperature, say lead lithium coolant. You've got to have a system where the parts that become damaged by the neutrons can be switched out quickly. You want it itself to be low radioactivity. And finally, as you work your way out in magnetic fusion, eventually you get to magnets, superconducting, or in some configurations, normal magnets. They have to be able to handle high magnetic fields. They have to have very low dissipation. They have high stresses on them. In the ITER configuration, it's about 12 Tesla at the highest field point, for example. And you want to be able to build those and build those cheaply. And so what are the kind of the specs on these things? The high heat flux components, if we can make 25 megawatt per meter squared components reliably, tungsten is okay material. It would be great if there were a carbon-based material that could be used there because it's really zero radioactivity. It's got to be able to withstand about 5 megawatt years per meter squared of neutrons. That's this number of neutrons. That's about, the materials community calls this displacements per atom. It's vastly more than the number of displacements by the primary neutron impact, but it is somewhat, and it is somewhat less than the total, I'm sorry, let's see, it is a lot more than the, it's a lot more than the, see if I can express this correctly. If you do the whole cascade, there are about 3 times less than this displacements. This is an overstatement. And then the initial neutron impact is way less. But in any event, you're displacing these atoms a fair bit. The tritium generating blankets have to handle a higher neutron flux because they're right up against the plasma. You'd like to get up to 1,000 degrees C, the obvious usual arguments. And you need a little bit more than 100% tritium regeneration. It's actually not like a fission breeder. The residence time of the tritium in the system is only a few hours, so it's not years, and so the reproduction time is not a big issue. You just need a little bit more than 100%. Magnets, superconducting and normal. The highest field possible from the physics point of view is desirable because fusion power, as it turns out, you go through the physics arguments, scales like the 4th power of the magnetic field. So you guys help us with superconducting magnets that can go to, for example, 20 Tesla at 1,000 amps per square millimeter in the non-copper part. That would change the picture dramatically. All of a sudden, the cost of these systems just plummets. About half the cost is in the magnets. We need very strong structures. The weight of the structure is not important for us. The volume of the structure is important. Super strong support structures if we're going to go to 20 Tesla. You want to change the world. Another way you can do it is improve normal magnets. If now we don't need all the shielding that you need for superconductors, you can handle a significant amount of heat. You can bring the magnets closer to the plasma. You can push up the efficiency of the system rather dramatically. If there were a material out there whose conductivity was copper or higher, that was able to withstand, say, 2 megawatt years per meter squared of neutrons, that was low activation, you start getting past those numbers, and you have a dramatic impact again on the cost of electricity from fusion and on the rate at which you could bring it online. So there's some pretty exciting things. I thought I'd put some numbers on the table. Just to talk about some of the things that have been done, the ferritic steels that were used for breeder reactors, were developed for breeder reactors, had in them materials that are not good for fusion. You don't care about the moly in a breeder reactor. The fission products, have killed you already, but way before you worry about the moly. But if you swap the moly for tungsten, you're in pretty good shape in terms of radioactivity, huge advantage in radioactivity, but it also turned out much better, much smaller issue of becoming brittle. Big win on brittleness. And indeed, the steels that we've developed with a more modern sort of nano approach to materials technology have better fracture toughness and better thermal conductivity as well. So some very attractive properties to these steels. There's nanocompositive ferritic steels that look like they can also go way out on stress versus temperature curves compared to the older oxide dispersion strengthened steels. These need to be tested in a neutron environment. We need to understand the ability to scavenge, in particular, helium that gets produced from the higher energy neutrons from fusion. A chart about what's needed here. I can see I'm getting to the end of my time. The big issue for fusion in materials, see the amount of DPAs are similar to the fission Gen 4, and indeed we've tested materials to these kinds of DPAs and they look okay. The real issue is that you get significant helium production. You need energetic neutrons. If you get energetic neutrons from fusion, they cause transmutation. You get some helium. You have to worry about the helium buildup in the materials. The Japanese think this is okay in their analyses. We also think it's okay, but you've got to test it. You want to do simulations to understand that. First principles calculations. This is actually a group in Princeton, not part of my laboratory, that's doing this. You want to understand the effects, the energetics of defects. You want to understand how those defects can migrate, and then you need to put that into your Monte Carlo studies and work your way up to the macroscopic structures of the system and its strength. You want to test that ultimately in a 14 MeV neutron environment, typically a dilithium stripping cell. You need to do this relatively quickly so you can bring fusion online. This is sort of part of the development path. So in summary, if we can make it work, I think this is an attractive energy option. Progress has been rapid, but it's limited by budget constraints. Let me tell you a story. In 1980, the Fusion Engineering Act of 1980 said, let's have a demonstration power plant in the year 2000. They said, let's triple the budget to do it. And it turns out Congress has a great memory. They remembered the factor of 3, but they put it in the denominator. So we have now 9 times less funding than they had projected in the Fusion Engineering Act of 1980. But in fact, the amount of money that we have spent today is the amount of money that in that plan would have brought us to the decision to construct ITER. So we're on the schedule versus dollars. Progress towards it has been budget constrained. Japan is spending about half again more than us. Europe is spending about twice as much as us. Probably one or the other will win the competition to site ITER. So there is a real issue that the U.S., if it's going to be competitive, has to grab some of the other things. We're not going to be building ITER. Are we going to optimize the fundamental understanding of these plasmas, the configuration optimization? Here's ITER that we have to be a participant in if we're going to compete in this market. How about some of the materials and nanotechnology issues? Are there some opportunities for us there so that we can be leaders ultimately? And nanotechnology is needed, is now being used already for the materials that we need, and could have revolutionary impacts, particularly through magnet systems because of that B to the 4th factor. So thank you.
Who wants the mic? All right.
If you just shout, I can answer any question.
Looking at your last slide there, Rob, what is the current betting on ignition in ITER? And I guess connected to that is, and what is the input power to ITER to get that fusion power that you talked about?
Okay. Let me answer the second question first. The ITER has been sized to have a gain of 10. meaning that there'd be about 50 megawatts of input power to the plasma for a fusion power of 500 megawatts. You need to do better than that in a power plant. If you want to work out all the efficiencies, you'd rather have 20 or 30. So it's a step. It's not the whole way. You would not actually run a power plant, quotes, ignited. You wouldn't want to turn off the control power anyway. You'd want to run it at sort of a gain of 25 or 30. So let me answer the question, what confidence do we have in this gain of 10 operation, which is what we've spec'd for it. One of the issues of this snowmass meeting was to really struggle through that question also. I mean, there were these two questions. If it works, is it what we want? And the answer was yes. And then the other question is, does it work? And we have struggled with that. And even there was you remember from your time in the Department of Energy, there were a collection of theorists who'd come to the conclusion that this was sort of a bust. Even they have decided that it looks okay. They say it's because the design is better. The experimentalists say it's because the theories have changed. There is some truth to both, and how much of which is not so clear. In my opinion, in fact, the theories have evolved. They've gone from what are called gyrofluid models to gyrokinetic models that are more accurate, that give you more optimistic predictions. And in fact, the design has been modernized. It takes a little bit of a aficionado to know, but the design is significantly different from a physics point of view. I think it's more the design myself than the theory change. And the fact is that now there is essential unanimity. You will find some folks that will say, no, it won't work. Bruno Coppi, to give you a for example. You know Bruno. But at this snowmass meeting with sort of 300 physicists, other than this particular Bruno, it was a 100% vote.
Thanks, Rob. As soon as this pops up, we were scheduled to have a 15-minute break. What we're going to do is take a 5-minute break. So if you're going to use the facilities, go quickly. You can go out and get a cup of coffee only if you promise not to talk to anybody on the way out or back. So we will reconvene with Terry Mikowski at 25 after, and you don't want to be late to hear Terry. We'll get started even while the computer is still getting its brain back here. The next speaker in this last session is Terry Mikowski from Sandia. We're now in the area of efficiency and electrical systems. Terry?
Okay, well, I want to thank everyone who's hanging in this long for the conference, and I also want to extend a special welcome to our viewers in the comfortable chairs. And you know who you are, so. Well, I was really excited when I got the invitation from Rick and Wade and Amy to join this conference. It's really a great event. But then after about 3 of Rick's slides, I noticed one where my topic of efficiency and conservation was in the small potatoes category. And as the conference went along, though, my feeling of personal hurt was evolved into great relief, knowing that I didn't have to stand up here and propose a credible technical solution to the really big problem. And frankly, looking at what I can see in the bag of nano tricks, I don't see any silver bullets that are going to shoot a hole in this problem. In fact, I don't see any single thing that's really going to change the situation. But what I do see, though, are very many challenges that are accompanied by all of these technological challenges and pathways that are in front of us here. And that I can't see a single one of those challenges that isn't going to be impacted by how the field of nanotechnology develops. And in a way, what I think our real challenge as nanoscience and technology people is going to be learning how to understand the significance of these different problems and focus on a few of them that can really make a difference. Because what I heard here today was everything's going to get fixed by nano. And if we go off in 1,000 different directions trying to do that, we won't make any impact at all. And so I'm really pleased to hear plans for a follow-up conference. But I think that's what this is a great start, but the next steps have to really start to evolve that, down select, and really understand where the priorities and differences can be made. Now, before I get into the details here, I want to make a little confession. That first, my confession is I'm a Mac user, so I'm intimidated by this thing. But the real confession is that we do this because it's just really a lot of fun. I mean, nanoscience is the coolest thing. And what is really interesting about it is not the fact that there are now synthesis tools and characterization tools and theoretical tools that allow us to work on this extremely small scale. I mean, that's okay. That's fine. But what's really exciting about it is that when you get down to that scale, completely new things happen. New properties, new behaviors emerge. And that's what's driving the scientific community around the world, figure out why people are so excited, why we have so many scientists jumping onto this field. And I show a few examples here of the kinds of things you can expect to see. That, for instance, you can take materials like silicon, which in their bulk state aren't very good light emitters at all, transform them by structuring down to the scale of a few nanometers into particles that are very efficient emitters of visible light. You can change the capability of catalysts, change chemistry. And this plot here shows about 3 orders of magnitude increase in the activity of a traditional catalyst as you scale from about 15 down to 2 or 3 nanometers in diameter. And you might say, well, that's sort of understandable because as I make the particle smaller, catalysis going on the surface, I'm just seeing an effect of a surface to volume ratio. But actually the blue curve there is scaled per surface atom. And so what it's saying is that when you make materials this small, fundamentally their properties change. And the last one there is the mechanical things. We've heard a lot about mechanical properties being important. Here's a case where you can look at the hardness of a material, in this case gold. It's something we think of as a very soft material in its bulk state. When it's structured on the nanometer scale, you can end up with hardnesses that are equivalent to a wear-resistant ceramic coating. So that's the excitement. There are just fundamentally new properties that emerge, and the exploration of those properties and the understanding of where they come from so that we can predict and build on that is what the field is about. Now, if I then take these kinds of properties, though, I can easily overlay them on some very important problems, technological problems, and in fact some that are very important to the Department of Energy. And these include energy and national security, environment. And I show a few examples here that I'll get into as I go through the talk, but where specific kinds of nanostructured materials, in the case of energy, I just show an example of a layered material producing very efficient light sources. Security, some nano-structured self-assembled membranes that are used for chemical sensing and detection. And then in the environment, catalysts and development of new chemical routes that are more environmentally friendly are all possible. What's really important here, though, is how do you take that nano property and translate it into a stoplight or a first responder's ability to measure the environment around them or into a better industrial catalytic process? And this, I think, is one of the big challenges that the nanoscience community has to face, is coupling these small scales across to the length scales where these properties and processes will be important. Now, one of the most important things being able to do that is that you have to be able to make the stuff. I mean, it's as simple as that. Nano is fine, but if you can't make the material in a high volume, reproducible, high reliability way, you're not going to impact these real world problems. And in fact, the examples there kind of give you a sense of where we stand with that. On the far left are these materials that are nano in one dimension only. So these are thin stacks, pancake stacks, where the pancake itself is about controlled to about 5 to 10 nanometers in thickness. And these are what we call strained layer superlattice materials. They allow you to build a crystal structure that doesn't exist in nature and use that property to control optical, electronic properties of the material. Now, when I was a young upstart at Sandia Labs some 20 years ago, that was a very emerging topic of science, was strained layer superlattice. We were really doing a lot of the theoretical work to understand what these materials would do, messing around in the experimental side of making these on a laboratory scale. Well, 20 years later, this is now a fully manufacturable material. And there are companies that build these, and in fact, when you drove here, you probably stopped at a stoplight that was made out of that nanostructured material, these funny-looking stoplights with all the little dots instead of the lens. If I look at that kind of manufacturing capability and say, well, where do I stand in terms of nanocrystals or self-assembled membrane three-dimensional materials, I would say we're at an extremely primitive stage. We're kind of where we were back at that 20-year point ago for the strained layer superlattice. And so a lot of important things here is picking systems that we can gain that experience and move rapidly along that curve to go from a laboratory kind of experiment to something that you can really make and really use. Now, let me show you a few examples, though, of when you do that, what happens, what can be gained from that. And I'll look at these layered materials first, because those are ones that we really have some experience with. And what they're, one of the applications is to build light-emitting diodes and lasers, you know, like this one here. We're all pretty used to this. They're in our CD players, they're in our stoplights, they're starting to show up all over the place. And the reason is that in the last decade, we've increased their output efficiency by a factor of 30 and decreased the cost by a factor of 10. They're starting to become things that are commercially available as we move up this curve of performance as a function of the basic science that's done in the manufacturing science. And what you see is that they're now getting up into this region where they compete with our traditional light sources of incandescent and fluorescent lighting. And for that reason, you're starting to see them. Sometimes. You're not seeing this one, so. That's actually Times Square, the NASDAQ, you know, that's a solid-state lighting display. You're seeing them in stoplights because they're 10 times more efficient than filtered red light, and they have lifetimes of about 100,000 hours. So there's two things about stoplights. One is they use a lot of electricity, and because they're on constantly. And the other thing is that it's a real pain to replace the light bulbs. And so they make an excellent application here. But what's interesting is you're starting to see them in more specialty applications. They're replacing different design features in buildings. They're being used in different ways. And I think it's important to, you know, look at how new technologies move forward. I know when I first saw the handheld calculator, well, that was kind of what I thought was going to come out of solid-state microelectronics. I never envisioned how intimately involved my life would be in this technology in ways I never imagined. And I think we're going to see the same kind of thing as this kind of technology moves forward. And so maybe someday when you walk home, your house will sense the mood you're in and adjust the lighting to, you know, soothe your day or whatever, but these are all things that are possible. I mean, we're using these incredibly inefficient lights up here because we like the character of the light. We didn't replace all these with fluorescent bulbs because we like this sort of soft lighting. This kind of technology is going to allow you to set in real time what that condition looks like and do it more efficiently than what we have now. So I think we're going to see not just replacing what we do, but opening new opportunities as well. And now in order to get there is part of what's called the Solid-State Lighting Initiative. This is a national initiative. And in fact, Sandia, Los Alamos, and Lawrence Berkeley Labs are working together on this to reach this target, which would put solid-state lighting at twice the efficiency of fluorescent lighting we have today. And in fact, if you achieve that target, the road mapping would suggest that although these aren't terawatt answers, there's still some pretty big savings that evolve from this, because we spend about half of our electricity, oops, is that right? No, I'm sorry. Half of our electricity on lighting. And if we can reduce that in half, we've got a 10% saving in our total electrical consumption in the world. And of course, that ends up being some pretty big amounts of energy and dollars in construction costs for the power plants we no longer have to produce, and large reductions in the carbon emissions. So these are things that can come from the development of that technology. These layered systems offer opportunities for other kinds of energy savings. Research groups at Argonne National Labs are looking at these layered materials to build exchange spring magnets. These are very hard magnets that are useful for highly efficient electrical motors. And what you see here is that the measure of their performance is very sensitive to how thick the layer is. Here you're at 200 angstroms, 20 nanometers, and here you're down to about less than 2 nanometer thickness. You get great improvements in the performance by being able to manufacture and control at this nanometer scale. Same is true in mechanical wear resistance, and this is some work going on at our labs where we're building composites that have structures that are on the nanometer scale. We can transform materials like aluminum, which is light and structurally good but not wear resistant, to have properties better than a wear resistant bearing steel through this nanocomposite structuring. Catalysis is another area now where nano-sized particles appear to have some real advantages. And I think we heard in one of the talks yesterday about it would be nice if we could get the nitrogen out of our gas feedstock, because we form nitrous oxides in a lot of this chemistry. Well, that's because of the temperatures we operate at. And if we can use catalytic processes to lower those temperatures, you can effectively remove the nitrogen side reactions without having to remove the nitrogen from the feedstock. So there are big environmental savings to be had here, and they seem to be focused very much on things that are in this nanometer scale. And this is some work of Wayne Goodman at Texas A&M, which shows that these clusters of gold have very strongly peaked properties when they're just 2 layers of atoms thick. Can't say we really understand why that is, but again, at that scale, some fundamentally different things happen that don't happen for single atoms and don't happen for the bulk. Nanoscaled texturing of surfaces. This is some work that is going on at the University of Florida, looking at building electrode surfaces. These are going to be important for advanced batteries, capacitors, for fuel cells, where nano-sized texturing actually provides improved electrical performance of that conductive electrode interface. And again, being able to go from a kind of laboratory experiment to really manufacturing stuff like this is where we have to go to make these savings really count. So when I look at nanomaterials, I can see very broad energy applications. Going all the way from these layered composites, where we see a lot of the benefit right now in efficient lighting, magnets, low friction surfaces, to nanoclusters and nanotubes for hydrogen storage, artificial photosynthesis. These are kinds of things that people are really looking at seriously now. To the nanoporous membranes, which are really 3-dimensional materials that could be important in chemical separations and filters and membranes for fuel cells. No limit, I think, to these kind of applications. The question is, what's it going to take to get from those materials to systems that really deliver that energy performance? And one of the things is I think that we're going to find is very important is that what it takes is the ability to integrate different length scales together. That there'll be very few solutions which are nano alone. That, oh, here's the bag of nano powder, just sprinkle it on your thing and everything will be good. The nano is going to be involved in some complicated engineering system, and it has to interface in how we manufacture it, how we get information in and out of it, how we get energy in and out of it. And I show that this is not really strictly an energy example. This is a security example of what we call a microchem lab. It's a handheld chemical analysis system that we've developed. In fact, these are deployed in subways and airports around the country right now. The whole device here is about the size of one of our name badges. It has two full gas chromatographs that can detect and analyze part per billion concentrations of nasty chemical things in complex backgrounds. All of the parts are really micro scale. So there's micro scale detectors and preconcentrators and separation columns. But what delivers the performance to this entire integrated package is the assembly of a nanoscale membrane which is attached to this preconcentrator. That membrane is made by a process we call self-assembly, where the individual molecular interactions actually drive the end structure. So we don't template that structure, it builds itself. And it can be controlled to the point where each of the pores is exactly the same size. So now when you're looking for a specific chemical, you can tailor that pore so it's the right size. And in fact, this nano membrane, which sits on top of this micro hot plate, provides about a 500-fold increase in the sensitivity of that overall device. If we didn't have that sensitivity, the whole device would be not applicable, not relevant, small potatoes to the problem at hand. Now, it probably shouldn't be a real surprise to us that this kind of integration across length scales is going to be an important part of how nano gets used. Nature, you know, it's like the consummate nano thing. We are the nano thing, right? Every sort of basic molecular, you know, function and chemical pathway in biological systems has its roots in some nanoscale machinery. But the functions are achieved in living systems by integrating these different capabilities together over multiple length scales. So these individual molecules assemble into larger structures of cell membranes and mitochondria. These guys assemble into larger yet structures that have more functions, like complete functioning cells, and cells assemble into tissues and tissues into organs, and pretty soon, you know, here we are. What's really fascinating about it, in a way, is you get down to this level, there are machines that do really neat things. There are molecular protein motors that have 2 feet and they walk along a track. And they take a 4 nanometer step every time they move. Those little machines are, I mean, a fabulous engineering feat on itself. But what I look at is the fact that a collection of those machines allows me to do that through an integrated architecture that spans multiple length scales. I don't think we're even close to understanding how to connect these length scales together. But to me, that architecture is going to be what really will be just as important as any other part of how nano evolves into something that makes a difference to the world we live in. So now I'm going to take, since I have no time left, my commercial part of the message here. But and just point out that you heard about it. Tom mentioned yesterday that DOE centers, and so did Dr. Russell, that there are a lot of centers growing up around the country around nano, and I think it's important to understand what these different centers might have to offer and how they're going to work together to go after these problems. We're developing one in New Mexico, which is joint between Sandia and Los Alamos National Labs. And it's one of 5 centers that the Department of Energy is building right now. Ours is focused on this issue of integration. All of the centers provide open access to a set of tools and capabilities for the user community. And in fact, I just quickly show the 5 centers which are being developed. They have 2 charters. One is to provide these tools, kind of like a synchrotron provides tools for people to use at no charge. So these centers will do that. The other charter, though, is to focus nanoscience activities around things that are important to the missions of DOE. And that's the part that I think, so the user part is here that says, you get to use this for free. All you got to do is apply and be reviewed in a peer-reviewed process, and you can have access to these tools. What's, I think, more important, and when we look at how different centers interact, these centers are really going to take a focus around DOE, science, and technology issues. And each of the centers has been using open workshops to begin to evolve and develop that focus, working with the user community. And so I just want to end by pointing out that if you just need to sit longer, you haven't sat long enough this weekend, and you're looking for an opportunity that in just a month from now we're going to provide one, and there's some pretty high-powered folks who are going to help us work through these discussions and develop, because we're very interested in how these centers can contribute to this challenge that's in front of nanoscience. I mean, we heard no end to the things that nano has to do in order for us to have an energy future. What we really need to do now is to take that deeper step of what can nano do and what are the really important focus areas that we'd want to use resources like these centers as well as other agency programs to go after those challenges. So anyway, I thank you very much for your attention.